The subject of this lecture is function representation. Before explaining in detail the function representation, let's consider its links with other 3D modeling techniques and approaches listed on the slide, and then we will discuss the reasons for the function representation. Function representation has following links with constructive solid geometry. It uses algebraic primitives of CSG and algebraic patches in constructive shells. Also, the same ray tracing algorithms are used for rendering. Link with boundary representation is using the same algebraic patches in modeling, and algorithms of polygonization which translate FRep models to BRep models. Link with sweeping is generalized cylinders with skeletal curves, which are used as primitives in 3D modeling. And link with voxels is polygonization algorithms, which translate FRep models to the voxel representation. The idea of representation of an entire complex object by a single real function is applied effectively in skeletal implicits. There are two main approaches for operations under primitives, which are represented by a single real-valued function. The first one is min-max operations, but they have usage limitations due to the C1 discontinuity. The second one is array functions, which don't have the above limitations. Connection with solid sweeps. There is theoretical possibility to derive an implicit description of a surface swept by a revolving solid. Attention is paid in computer-aided geometric design to implicit surfaces because of their closure under such important operations as offsetting and blending. Several deformations available for implicit objects such as twist, bend, taper, and free vibrations. In addition, there is a collision detection algorithms for implicit surfaces. Similar polygonization algorithms stress common nature of implicit and voxel models. Existing the metamorphosis operation for skeletal implicits and for voxel representation in schedule Fourier volume morphing also underlines their link. We can make the following conclusions. Representations by real-valued functions are widely used in geometric modeling and computer graphics in several forms. These models are not closely related to each other. These models are not closely related to such well-known representations as CSG, BRep, sweeping, and spatial partitioning, voxel models. An uniform function representation is needed to fill these gaps. This representation has to unify all functionally based approaches, be convertible from other representations, be dimension independent, have as rich as possible a system of operations and relations. Geometric concepts of a functionally based modeling environment are represented by the following tuple, where M is a set of geometric objects, F is a set of geometric operations, W is a set of relations on the set of objects. Mathematically, this triple is a sort of algebraic system. In the next few slides, let's consider the objects in function representation and their properties. Objects in FRep are closed subsets of n-dimensional Euclidean space with the following definition, where f is a real-valued continuous function defined on this space. Classification of points in n-dimensional Euclidean spaces is following. Inequality f of x greater than 0 is for points inside the object. Equation f of x equals 0 is for points on the object's boundary. And inequality f of x less than 0 is for points outside the object. Here x is a point with n coordinates in defined n-dimensional Euclidean space. In 3D space, the boundary of such an object is a so-called implicit surface. The function can be defined analytical expression, function evaluation algorithm, and tabulated values with an appropriate interpolation procedure. The major requirement to the function is to have at least C0 continuity. The objects must be defined by the inequality with the explicit function of n variables, but not the implicit function of n-1 variables. Multidimensional space with order greater than 3 can also be used for modeling. As example, space-time modeling with 4 independent variables, where 3 variables are space coordinates and fourth one is time. The difference between primitives and complex objects is that a complex geometric object is a result of operations on primitives. Objects in FRep are extensible. It means users can introduce their own new primitives. There are following types of FRep primitives. It's algebraic surfaces, skeletal objects such as soft or blobby objects, and so on, convolution surfaces, radial basis functions or volume splines, trivariate B-splines, voxel array plus interpolation, and procedural. On this slide you can see examples of different types of primitives. The complex object of FRep is shown on this slide. There are two main classes of operations in FRep. It's unary operations for one operand and binary operations for two operands. A binary relation is a subset of the Cartesian product of a geometric objects set. It can be defined as following. The examples of binary relations are inclusion, point membership, interference, or collision. Point membership relation classifies point P into three classes: the interior of geometry, the boundary of geometry, and exterior. Examples of unary operations are following. It's bijective space mapping or deformations, offsetting, projection, and sweeping. Here is one example of the deformation, which is called twisting. This is example of Fuyuchi-based mapping. And this is example of Fuyuchi-based mapping too. Here is example of the unary operation, which is called offsetting. This is an example of the Fuyuchi-based offsetting. This is an example of the unary operation, projection. This is an example of the sweeping operation. And finally, example of the hypertexturing operation. The binary operations of FRep are following. These are set-theoretic operations such as intersection, union, difference, and operations of blending and metamorphosis. Let's imagine that we have two objects, G1 and G2, which are defined by two inequalities with two functions, f1 and f2, as shown on this slide. For performing the set-theoretic operations on these two primitives, we need to find such special functions which save the signs of the original objects according to the type of operations. These special functions for the set-theoretic operations can be R functions. The notation of different types of R functions are shown on this slide. The theory of R functions was introduced by Vladimir Rvachev and found many fields of application. This theory describes the principles of performing Boolean operations on functionally defined geometry. The R functions in the common view are represented for three set-theoretic operations on this slide. But in practice, the most useful forms of R functions are obtained when the alpha parameter is equal to 0. These functions have C1 discontinuity only in points where both arguments are equal to 0. The obtained functions are shown on this slide. For higher order of C continuity, the following set of R functions may be used. On this slide you can see an example of FRep modeling, presented as a tree. All complex FRep objects have such a construction history tree. This slide shows R function contours with different contouring thresholds. You can see that contour with straight intersection has 0 threshold. Other contours are smoother. Blending operation allows to mix primitives. The statement for this binary operation is shown on this slide. By changing parameters a1 and a2, we can get different results of the operation and control addition or removal of material. You can see on this slide the example of intersection operation with different values of parameters a1 and a2. On this slide you can see the advantage of R functions as set-theoretic operations in comparison with min-max functions. When we apply blending operation to the object produced by min-max operation, we can get such artifacts as unwanted edges, middle picture on the slide, while the R functions gives good result, right picture on the slide. This is an example of the blending union operation. On the previous few slides, the blending operation is uncontrolled. To get a controlled blending operation, we need to change the displacement function with conditions shown on the slide. It's called bounded displacement function, and operation is called bounding blending. Here is an example of bounding blending operation. You can control the place and size of blending area as shown on this slide. We can use bounding blending operation as Unary operation and apply it only for one primitive. It's called partial edge blending. Another one important operation in FRep is metamorphosis. This operation allows to construct intermediate shapes automatically during transformation from one object to another. The statement for the metamorphosis operation is shown on this slide. Let's sum up what is function representation or FRep. It is uniform representation of multidimensional solids defined as inequality with function of several variables. Function f of x is evaluation procedure traversing the construction tree structure. Construction tree consists of the leaves with primitives and nodes with operations and relations. Also, FRep has empty case principle and it is extensible. There are several implementations of FRep approach as software tools. The list of these software systems you can see on this slide. FRep is multidimensional representation, therefore it allows to model heterogeneous objects. Heterogeneous objects are objects with internal structure with non-uniform distribution of material and other attributes. Such objects can have different dimensionalities and varying material distribution. Heterogeneous objects can be used for physical simulation, geological and medical modeling, volume modeling, and rendering. For description of the heterogeneous objects, let's introduce the constructive hypervolume model. It consists of the geometry described by FRep and attributes described by FRep2. The constructive hypervolume model has independent representation, but uniform treatment both for point set geometry and for attributes. Geometry and attributes are constructed using primitives, operations, and relations, and real-valued functions or scalar fields are used for it. Here you can see an example of the hypervolume model construction. On the left image the geometry is represented. On the right image the attribute space partitioning is represented. By combining these two parts we can obtain a complex heterogeneous object with a different distribution of materials or properties inside. Here is an example of the heterogeneous object built using constructive hypervolume model. Here is a list of references to key publications on function representation.